Okay, good morning, lads and ladies. Welcome back to MAC 1140. You are now through the second exam, so congratulations on persisting. Today we're going to begin the third part of the course, which is on exponential and logarithm functions. And this is sort of our last unit where we're studying specific functions. So after that, we're going to start talking about a few kind of different topics. We're going to talk about systems of equations and matrices, series. But we got to wade through the quagmire of exponentials and logarithms first. I'm sorry, I'm definitely feeling a little bit sick this morning. So if you have a hard time hearing me or anything, don't be shy about asking me to repeat myself or speak up. Okay, let's get the screen share going and start doing the thing. Okay. All right. Let's peel some of this off. So of course this is, as always, AC 1140. Section number is, which means we're talking about pre-calc. And today is the 27th of October, 2021. I don't know if you guys are in Gainesville today, but it is a beautiful day. So on this beautiful day, we're going to be introducing exponentials and logarithm functions. So yeah, that's the game. My favorite way to introduce this topic is with some simple examples that you will have some intuition for, most likely. Let's see, you do want to grab your book. Missing up the theorems. Okay. So logarithms are going to take a little bit of time to get to. Basically, we're going to start by talking about exponential functions, and these things show up in so many different places in the real world that, like I said, we can introduce them with some very intuitive examples. Logarithms are the inverses of exponential functions. So after we kind of talk a little bit about exponential functions, in order to introduce the logarithm, we're going to need to remember that stuff from section 2.8 on inverse functions. So if that was a section that you were a little bit hazy on, or a section where you didn't get to spend a lot of time in the homework, you might want to go back and rework some of those homework problems from section 2.8. Remember, you can always request an extension in WebAssign. So if for whatever reason you feel like inverse functions didn't quite click for you, don't hesitate to do that. I'll be happy to open those up so you can spend some time there. Or of course, you can come talk to me in office hours. I think before I give you the definition, let's just look at an example. Suppose you guys, maybe before I get into this, how many of you have read the book Of Mice and Men? Just give me a thumbs up react, or any sort of react here in Zoom if you're, for example, in high school forced to read the book Of Mice and Men. Used to be a standard thing, maybe not so much these days, but just Shauna. All right, so if you haven't read any John Steinbeck, Of Mice and Men is probably the most accessible. It's very easy, but maybe Shauna will be the only person to get the bad joke I'm going to build in here. So suppose Lenny has one rabbit on day 0. on the next day, George gives him another rabbit. And warns that the number of rabbits will double every day after that. All right, so George has his one rabbit, and the book ends the way it would have been nice to end for George and Lenny, and they get a little farm. On day 0, Lenny has just the one rabbit. On day 1, George gives Lenny another rabbit. So on day 1, George has 2 rabbits. And every day after that, the number of rabbits they have are going to double, because that's what rabbits do. They make more rabbits. Can we find a function which tells us the number of rabbits on George and Lenny's farm after X days? Right, so that's the deal. Day 0, 1 rabbit. Day 1, 2 rabbits. And every day after that, the number of rabbits is going to double. So if I want to find a function that tells me the number of rabbits after X days, maybe I just start by figuring out how many rabbits there are on the 3rd day and 4th day and look for a pattern. Let's call this function f of x. And this is the number of rabbits on day X. I'll make a little table. We'll write down a few values, and then we'll look for a pattern and see if we can write down a formula for this function. We said on day 0, 1 rabbit. The next day, George gives Lenny another rabbit. So on day 1, there are 2 rabbits. How many rabbits are there going to be on day 2? Anybody? Don't be shy.
4.
4, right? Because every day after this, the number of rabbits doubles. So there are 2 rabbits the previous day. So we're going to double that to 4 on the next day. And on the 3rd day,
8.
8, right? Because every day the number of rabbits is going to double. All right, just one more. On the 4th day, how many rabbits?
$16.
16. Thank you. Okay. And what's the pattern? Well, to go from here to here, you double. 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 let me rewrite some of these numbers in ways that are slightly more suggestive. So the next day, on the 5th day, there would be 32 rabbits, right? And the 6th day, there would be 64 rabbits and so on. First, let's just observe that 2 is 2 to the 1. 4 is 2 squared. 8 is 2 cubed. 16 is 2 to the 4. And it also happens to be true that 1 is 2 to the 0. So looking at this pattern, how many rabbits do we expect to see on the X day? Day 0, there's 2 to the 0. Day 1, there's 2 to the 1. Day 2, there's 2 to the 2. Day 3, there's 2 to the 3. On day X, there should be how many?
2x.
Yeah, 2 to the X, right? So that's the formula for f of x. That's the number of rabbits that will be on the X day. And what this means is that George and Lenny are in trouble. Not the kind of trouble they get in Steinbeck's book, but a different kind of trouble. Because this function grows very, very quickly. You've heard the statement that you cannot possibly fold a piece of paper over in half like some number of times, right? I don't know what it is, 7 times, 6 times. That if you're able to fold a piece of paper in half like 15 times, it would stretch from here to the moon. That's because the thickness of the paper would double every time you fold it, meaning the same pattern would show up here, right? So even if you start with a number that's astronomically small, like the thickness of a piece of paper, after something like 15 doublings, if you go down to the 15th row here, this number would be larger than the distance from the Earth to the moon. So the first thing I want to observe about this function is that it grows incredibly quickly. In particular, it grows much faster than x squared or x cubed or even x to the 100. The graph of this function we want to, we can plot it. Mark this up here as 16, 8, 4, 2, 1. 1, 2, 3, 4. When x is 0, f of x outputs the number 1. So this will be the graph y equals f of x, where f of x is 2 to the x. When x is 1, this function outputs 2. When x is 2, this function outputs 4. When x is 3, this function outputs 8. When x is 4, this function outputs the number 16. You can also look at this function for some negative values of x, although it wouldn't have anything to do with the rabbits at that point. But if you were to plug in -1, you'd get 2 to the -1, which is 1/2. If you were to plug in -2, you get 2 to the -2, which is 1/4. -3, you'd get 1/8, and so on. So this function wants to get really, really close to 0 as you go off to the left. In fact, it has an asymptote the line y equals 0. But it only approaches that asymptote on the left. And over here, the thing basically goes straight up. Now, it doesn't literally go straight up. That would mean it's not a function anymore. Remember, functions have to pass that vertical line test. But it gets so steep over here that it's hard to tell the difference between this thing and a vertical line just by looking at it. And I'll show you what I mean in Desmos. Here you see the same shape that we've drawn. If we zoom out a little bit, look at this son of a bitch. Going like straight up, like really crazy. Genuinely looks like it's going straight up, doesn't it? And like I said, let's compare this to some other functions we've looked at, like x squared. At first, it looks like x squared might be growing a little bit faster. But as soon as you get out here, you see that this red function destroys x squared, like to a point where it's not even close. You know, if you drift out here a little bit, take your favorite x value, like x equals 15, and compare f of 15 and g of 15. F of 15 is 32,000. G of 15, 15 squared is 225. If you look along the line x equals 15 to try and find how much bigger the red is than the blue, you have to zoom way, 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 way out, like way out. Like still not even far enough, way out. Almost there. There it is. So when x is 15, the red function is right here, and the blue function is so much smaller, I can't even see that, right? There it is. Here. So 2 to the x grows way faster than x squared. And changing that x squared to an x cubed or even x to the 100 doesn't really alter this picture that much. Yes, x cubed grows faster than x squared, but not by enough that it will beat this guy. And same is true of x to the 100. X to the 100 grows a lot faster than x squared or x cubed, but 2 to the x will still destroy it. Why does 2 to the x grow so much faster than any of these polynomial functions? What is it about this function that makes it fundamentally different from these guys? And that is a genuine question. Really want to know what you have to say. What is it about 2 to the x that makes it so different from these power functions or polynomial functions, stuff like that we've studied earlier?
Is it because it has no x value, like it grows infinitely?
We're getting there. So actually, all of these polynomials kind of grow infinitely, right? So x squared or x cubed, they all grow, and they all grow to become as large as you like. But for some reason, the red function grows much faster. So here, eventually you'll see the red overtake the green. There it is. Now the red is bigger. So it's true that they all grow to infinity, right? If you look at the end behavior for any of these functions as we run off to the right, they're all going up. But why does the red go up so much faster? And it may help to think about the algebra, right? Kind of algebraically, what is different between stuff like this and stuff like this? What about them, like, literally physically looks different? Look at where the variables are. So with these guys, the variable is down here in the base, and the power is a constant power, variable base. So when you're looking for outputs of functions like these, you're taking a bunch of different numbers, the x values, and raising them to a constant power like 3. So here, if I wanted to plug x equals 5 into this, I would multiply 5 by itself 3 times. If I want to plug x equals 10 into this, I would multiply 10 by itself 3 times. Here, the base is a constant, and the variable, or the power, is a variable. So if I wanted to plug 5 into this, I would multiply 2 by itself 5 times. If I wanted to plug 10 into this, I'd multiply 2 by itself 10 times. So here you're taking a variable power, sorry, a variable base and raising it to a constant power. Here you're taking a constant base and raising it to a variable power. So kind of the neat observation is that powers, right? It's the size of the power that kind of dictates how fast these things grow. Here, the power is your variable. So the size of the power grows with your variable. And we know that powers are kind of a more powerful operation, right? It's pardon the pun. But if you raise a number to a larger and larger and larger power, that's a very sensitive operation. As that power gets bigger and bigger, the number gets bigger and bigger very fast, versus taking your variable and raising it to a constant power. So here with x squared, for instance, you're always just taking your input and multiplying it by itself twice. But here, you're taking the number 2 and multiplying it by itself x number of times. So if x is big, you could be multiplying 2 by itself 15 or 20 times. So the answer here in 2 to the x, the power is your variable. And in x squared, for example, the power is constant. You could say raising to large powers is a much more severe operation than multiplying a number by itself twice. In other words, the real reason here variable powers are much stronger than constant powers. That's the idea. So here where 2 to the x, your variable is the exponent. Here in x squared, the exponent is a constant. Even though this base could get quite large, you're still just multiplying that number by itself twice. Here, even though the base is 2, which is not an especially large number, when you multiply a number by itself like 20 or 30 fucking times, that's going to be enormous, even if that number is 2. Right here, you're talking about doubling every time x goes up by 1. This guy doesn't even come close to growing that fast. Right? Think about x equals 3 to x equals 4. When x is 3, this thing is 9. When x is 4, this thing is 16. 16 isn't as big as the double of 9. The double of 9 is 18. So this guy doubles every time x goes up by 1. This doesn't do that. This does something substantially smaller than that. If you think about, like, I don't know, x equals 8 to x equals 9. When x is 8, this thing is 6. When x is 8, this thing is 64. When x is 9, this thing is 81. So you can compare the rate of change. With x squared, the average rate of change from x equals 8 to x equals 9 is 81 minus 64 over 9 minus 8. And about how big is that? Well, this numerator is less than 20, right? If this was 84, that would be 20. So this is 3 smaller, is 17. For 2 to the x, that same average rate of change. I'm actually going to need some help calculating this. Let's see. What is 2 to the 8? 2 to the 6 is 64. 2 to the 7 is 128. So 2 to the 8 is 256. Which means 2 to the 9 is 512. So 512 minus 256 is 256. Right, so if you look at the slope, of the x squared function just from x equals 8 to x equals 9, that slope is 17. It's growing pretty quickly, meaning every time we take a step over by 1, we're going up by about 17. It's an average, remember. But on 2 to the x, when we take that step over by 1, we go up by 256. So the rate of change for 2 to the x is much bigger than 4x squared. And there's nothing special about 8 and 9. I just picked those numbers out of the air as fun things to play with. Compare. Yeah, sorry. So Joyce asked, what's this word? I apologize for my bad handwriting. Compare the rates of change. Okay. Functions like 2 to the x are called exponential functions, and they're called exponential functions because the variable is in the exponent. All right, so the naming convention makes sense. The variable is the exponent. We call it an exponential function. Here, the number a is called the base. We require a to be greater than 0. If a was less than 0, if a was a negative number, like say -2, then -2 to the x would have all sorts of problems. Like what would happen when you plug in 1/2 for x? Well, then you'd be taking the square root of -2, which is certainly complicated. It involves the number I, right? So we require a to be greater than 0 to avoid imaginary numbers. Imaginary outputs. I want this function's domain to be all real numbers. If you let the base be a negative value, then the domain is going to get very choppy, right? Like I can take -2 and raise it to the first power, third power, 10th power, but raising it to the 1/2 power gets complicated. Raising it to like the pi power, like what the hell is -2 to the pi? That's on its own a complicated question. So the base has to be positive. Otherwise, we end up with all sorts of trouble involving complex numbers. We also like for a to stay away from the number 1. 1 to the x is not a very fun function, right? Because if you raise 1 to some power, it's always just going to be 1, but that's not a big deal. Okay. We looked at 2 to the x, some other examples. Examples of exponential functions. So here the base is 2. Here the base is 3. And here the base is 10. All of these would be exponential functions because all of them are just a constant raised to the x. In this section, we're going to talk about the graphs of exponential functions, and we're going to talk a little bit about transforming them, right? Like flipping them over or shifting them left or right or up or down. And we're going to talk about evaluating them because it turns out evaluating these can actually be a little bit wonky. And then we'll talk about classifying them according to whether they grow or decay. Some applications. So first silly example, just going to see how well we remember the rules for exponents. So remember back in college algebra or wherever you learned a bunch of rules for working with powers. Let f of x be 3 to the x and evaluate f of 5, f of negative 2/3, f of pi, and f of the square root of 2. Let's start with the easy one. What is f of 5 here? You don't have to simplify it. Just tell me, how would I find f of 5?
You could just multiply 3 times 3 times 3 times 3 times 3.
Yeah, it's 3 to the 5, right? I'm just plugging in for x. Right, and Sean is correct in saying that this would be 3 multiplied by itself 5 times. Now, 3 squared is 9, times 3 is 27, times 3 is 81, times 3 is 243. I think. Pretty sure. But that's the only one where I'm going to be able to give you a nice output, nice answer. And one of the first things we need to kind of accept is that raising a number to a power can be thought of as multiplying that number by itself that many times, but only if that power happens to be a whole number. If that power is a weirder number like negative 2/3 or pi, then this is going to be a little challenging. That isn't to say we can do nothing. How would I get started here? Just writing down f of negative 2/3. Don't worry about coming up with this, just talking about coming up with this. So f of 5 is 3 to the 5. F of negative 2/3 would be what?
Three to negative 2/3.
Yeah, exactly. 3 raised to the power negative 2/3. Okay, and then we stop for a minute and remember, oh yeah, we do know a little bit about this stuff, right? Raising a number to a fraction, that has something to do with roots and powers. Raising a number to a negative power has something to do with like fractions. So what are the rules here? Well, the negative tells you this is the same as 1 over 3 to the positive 2/3. Right? Negative powers are reciprocals. I'll write down the rules in a minute, but I'm just trying to see what you remember. And then how do I raise a number like 3 to the 2/3 power? Well, this bottom here, this has something to do with a root. And this guy up here has something to do with a power. So this would be 1 over, that's this 1 over. And then 3 to the 2/3 is the cube root of 3 squared. That's how fraction powers work. Three squared is 9. So this is 1 over the cube root of 9. But the cube root of 9 is not an especially nice number, right? It's an irrational number. 9 is not a perfect cube. 9 is a perfect square, but it's not a perfect cube. We can ask our favorite calculation tool, what is the cube root of 9? Here, actually, Desmos doesn't know a nice way to type that. It's about 2.08. And that makes sense because the cube root of 8 is exactly 2. 9 is a little bit bigger than 8. So this is like 1 divided by, I should say shaky equals sign, approximately. 1 divided by 2.08, which is itself about, well, it should see 1 divided by 2 would be 1/2. So it should be a little bit smaller than 1/2. And in fact, it's like 0.48. 0.4807-ish. But not a nice number, right? We can get to here by hand pretty easily, but to pass to any of this stuff is a little tricky. By tricky, I mean not something you can do by hand. And these last two are going to be much, much worse. F of pi, that would be 3 raised to the pi. And intuitively, I can guess that this is going to be close to 3 cubed, which is 27, because pi is pretty close to 3, right? Pi is 3.14-ish. But we can't do a whole lot better than that. And the truth here turns out to be a little bit bigger. It's 31.54-ish. But you're not going to get it without a calculator. So this, I would say this is about as good an estimate as we're going to get by hand. And f of the square root of 2, similarly challenging. This is 3 to the square root of 2. I know that the square root of 2 is around 1.4, so this should be close to 3 to the 1.4, whatever the hell that is. But I don't know what that is. It turns out, again, by the use of a calculator, this is about 4.7. 4.728-ish. I guess the next figure is another 8. So if I'm rounding, it would be 4.729. We'll go ahead and give this. So an unfortunate fact of exponential functions is that it's kind of hard to plug certain numbers into them. Right? Like if I wanted to plug -2/3 into a polynomial, we could actually crunch that out by hand, and I could give you an answer that is a nice fraction. But many of these outputs are irrational. Let's see, do I have another color? So, many of these outputs this one, this one, this one, irrational numbers. Hence, difficult to calculate. By hand. And in fact, what we're really doing here, kind of secretly, I'm introducing a family of functions which are called transcendental functions. How many of you guys have you heard the word transcendental before? It means they transcend, right? To transcend is to sort of move beyond. Now, in mathematics, transcendental numbers are irrational numbers that are not like square roots, right? So the square root of 2 is an irrational number, but 3 raised to the square root of 2 is a transcendental number. Transcendental numbers are irrational numbers that do not show up as the root of any polynomial with integer or rational coefficients. And transcendental functions are functions that like to output transcendental numbers. Exponential functions are a type of transcendental functions. If you look at the calculus book that you guys will be using next semester, I get the very first page here. Here's the cover. All right, this is the book that we use for Calc 1, 2, and 3 here at Santa Fe, same book at UF. You'll notice it says early transcendentals. What that means is that this book introduces transcendental functions like exponentials early. Those of you, and by early we mean like at the start of the book, they don't wait until later to develop transcendental functions. Other examples of transcendental functions you guys have seen if you're taking trigonometry: sine, cosine, tangent, secant. All of your trig functions are transcendental functions. Okay. Before we go any deeper into this, I need to just remind you the rules for exponents, so in case you've forgotten that. If I take a to the x times a to the y, so I'm multiplying like bases with different powers, this is the same as a to the x plus y. If I take a to the x and I divide it by a to the y, if I divide like bases, I can also write that as a single power. That's a to the x minus y. And you can think of both of these as coming from this idea of multiplying a number by itself. So like a to the x would be a times itself, x times. A to the y would be a times a times a, y times. So when you multiply those, you have a times a times a times a, x times, next to a times a times a times a, y times, which is a multiplied by itself, x plus y times. Same thing happens here. You could cancel, basically, if you've got a multiplied by itself x times upstairs, a multiplied by itself y times downstairs, then you could cancel out the y, the a to the y stuff. You can cancel out the a's from the bottom, and you'd be left with a fewer number of a's upstairs. How many fewer? Y fewer. So if you had x copies of a upstairs, y copies of a downstairs, and you cancel all the copies downstairs, you'll be left with x minus y copies of a upstairs. These are the two most important relations for exponentials, but there are many, many others. One that people have trouble with, and that we will actually use quite a bit, is that if you take a power like a to the x and you raise it to a power, this is a multiplied by itself x times, and then that whole thing multiplied by itself y times. So that's y copies of a to the x, which is x times y copies of a. And these three are the fundamental three, right? These three things actually are sufficient to define the property of having an exponent. But there are some others. So let me just show you sort of the stuff we're using here. Call this 4. A to the negative x, if you raise some base to a negative power, that's the same as 1 over a to the positive x. So negative powers are reciprocals. And I'm going to use different letters here. A to the m over n, because usually when you see stuff like this, m and n are whole numbers. X and y are usually thought of as real numbers, could be whatever. This is the nth root of a to the m And because of this third rule here, that's the same as the nth root of a all raised to the m. So if you're asked to compute something like 3 to the 2/3, you can say that that would be the cube root of 3 squared. Or if we wanted to, we could say that that is the cube root of 3 all squared. So this square could be inside the root or outside the root. That's what we're saying here. Okay, am I forgetting anything? I think these are the stuff that we're going to need. These three in particular, we're going to be using a lot. Okay. Hold here just for a second in case anybody's still writing. All right, let's look at some graphs. Since we really don't know much else about these things right now, we're just going to graph these by plotting points. And then I will make some generalizations. And I am going to plug in some negative numbers as well as some positive numbers. Let's start with this. So when x is -2, 3 to the x, that's 3 to the -2, which is 1 over 3 squared, or 1/9. When x is -1, we have 3 to the -1, which is 1/3. When x is 0, we have 3 to the 0. What is 3 to the 0?
Zero.
Interesting, good guess, reasonable. 3 to the 1 is 3, right? So 3 to the 0 should be
Must be
3.
1.
Yeah, it's going to be 1. Should be 3 to the 1 divided by 3, which is 1. And a quick note here. A to the 0 is equal to 1 for any number A except 0 itself. 0 to the 0 turns out is undefined in a weird way. All right, 3 to the 1, that's 3. And 3 to the 2, 3 squared, that's 9. And what you notice is kind of as you go from here to here to here to here to here, you multiply by 3, right? 1/9 times 3 is 1/3. 1/3 times 3 is 1. 1 times 3 is 3. 3 times 3 is 9. So just like our first graph, the 2 to the x graph, where the height doubled every time you went over to the right by 1, here the height is going to triple every time you go to the right by 1. So the graph of this function we'll call this 9. Should make this around 3, which would make this around 1. I'll go 1, 2, 3, 2, 3, about like this. What do you notice about these outputs, by the way? What don't you see anywhere here? Maybe I'll come back to that. That's a pretty open-ended question. So here's -3, -2, -1, 1, 2, 3. When x is -2, we have 1/9. That's like tiny, tiny, tiny down here. 1/9, very small. When x is -1, we have 1/3. That's bigger, but still pretty damn small. When x is 0, we got 1. When x is 1, we got 3. And when x is 2, we got 9. So this graph looks a lot like our first graph did. It's doing something like this. And pretty quickly, he starts to turn around and look like he's going straight up. But over here, as we run off to the left, he's sitting down on this x-axis really friggin' hard. So again, we have a horizontal asymptote, y = 0. Here, we're blowing up, almost going straight up. This is the graph, y = 3 to the x. Looks a lot like the graph of 2 to the x, doesn't it? Very, very similar. It's a little bit steeper over here. And he sits down a little bit harder on the x-axis here. All right, that wasn't too bad. Let's do 1/3 to the x. I'll use the same inputs, -2, -1, 0, 1, and 2. If I raise 1/3 to the -2nd power, this would be 1 divided by 1/3 squared, which is 3 squared, which is 9. It's like the enemy of my enemy is my friend. The reciprocal of my reciprocal is me. Similarly, 1/3 to the -1, that's just the reciprocal. That's 3 to the 1, or 3. One-third to the 0. Anything to the 0 is 1. One-third to the muted. All right, there we go. We're back. Sorry, my Fox cable can go fuck themselves. So where were we? We were computing this table for 1/3 to the x. We graphed 3 to the x. Now we're graphing 1/3 to the x. 1/3 to the -2 is 9. 1/3 to the -1 is 3. 1/3 to the 0 is 1, because anything to the 0 is 1. And 1/3 to the 1 is 1/3. 1/3 squared is 1/3 times 1/3. That's 1 times 1 over 3 times 3 is 1/9. So if I want to draw this graph, and I'll put 9 up here, which will make this about 3, which will make this about 1. So when x is -2, we're all the way up here at +9. When x is -1, we're up here at 3. When x is 0, we are here at 1. When x is 1, we're down here at 1/3. And when x is 2, we're way down here at 1/9. So here my graph. Just connect the dots. Looks like this. And as we run off to the right now, this thing is trying to sit down very hard on the x-axis. And over here on the left, it's trying to go straight up. Just for the record, the next y value, if we look on this first graph, if you were to plug in x equals 3, that would be 3 cubed is 27, would be way off the page, right? Like not even up here, like way off the page. We'd have to multiply this height by 3. So 1, 2, 3. Same thing is true over here. If I were to try and put the next point on this graph, I have to multiply this height by 3. So that'd be 1, 2, 3. The next point, the point where x is -3 on the bottom graph, would be way the fuck up here. So we're limited in how much of these graphs we can draw because they grow so very quickly. The second graph also has a horizontal asymptote. This guy is sitting down on this x-axis really hard. The horizontal asymptote is also y equals 0. And what I'd like to do is start trying to make some observations and generalizations about these things. So now that we have both of these graphs, I'd like to ask you for the domain and the range. Okay, just looking at these graphs and thinking about how they continue in both directions. What is the domain?
Isn't it negative infinity to infinity?
It is, yeah. This arrow points out there and goes that way forever. This arrow points up here, but it goes on and on and on forever. And if you look at the graphs we had in Desmos, it's the same shit, right? Like, goes on and on forever this way. You see the blue just sitting down on that x-axis really hard. And you can go as far as you want to the right. Also, it just goes up really, really, really fast. So the domain for both of these is all real numbers. And this is true for all exponential functions. What about the range? What sort of y values do you see on this graph? On this graph. We can look at the Desmos graph if it helps. What sort of y values do you see here? Don't think too hard about this. I promise it's not tricky.
Zero to infinity?
Yeah, positive y values, right? And that's the question I was asking earlier. What sort of y values do you not see there? Negative ones. Now you never hit 0, right? When I come over here and I drag the mouse far to the left, you'll see it does say 0. That's a rounding error, right? 3 to the negative 15 is so small that Desmos can't tell it apart from 0. Maybe if I zoom in enough, it'll try. Yeah, it'll try, but we never actually hit 0. So we approach this horizontal asymptote, we approach this horizontal asymptote, but we never get there. This is also the same for all exponentials. What else do you observe about these? Look at that first one, for example. If you had to describe this graph to somebody like your grandma, somebody who doesn't know anything about algebra, and you had to tell them what this shape looks like, what is it doing, you know, how would you describe it? Think about the language we've used in the course so far, the sort of language that regular people know. If I picked you up and set you down on this graph and told you to walk left to right, would you be stoked about that? Or would that be a difficult walk? I know this is Florida, we don't have a lot of hills here. This would be a bitch of a walk, right? Because it's very much always uphill. This first guy is always increasing. And similarly, this second guy, strap some skis to your feet. You're going to be flying like a motherfucker down this thing, because he is always decreasing. And this is another property of exponential functions. If the base a is bigger than 1, then the function f of x equals a to the x is always increasing. We call this exponential growth. It's not just that it's increasing according to a certain pattern, where the height gets multiplied by some number every time you take a single step to the right. So as I take one step to the right from here to here, I've gone up by a factor of 3. As I take one step to the right from here to here, the height goes up by a factor of 3. That's not a slope, right? It's not going up by 3, it's multiplying by 3. And that's what we call exponential growth. And in the same vein, if a is smaller than 1, then the exponential f of x equals a to the x is always decreasing. And the particular kind of decreasing we call exponential decay. So these are some of the most important properties of exponential functions, this stuff down here in black. Something that is encapsulated in this statement that the range is the open interval from 0 to infinity is that these things are never 0. And it's almost worth stating on its own. You can say a to the x is never 0. It's also never negative. But this fact that you can't take a number like 2 or 3 or 5 or 1/5 and raise it to some power and get 0 out. That never happens. Okay. The last thing I'd like to observe about this pair of graphs has to do with a symmetry. What do you notice about the symmetries here? If we were talking about transformations and I asked you, how do you get this graph from the first graph? What would you say? What transformation would you apply to the first graph to get the second graph?
Flipped across the y-axis.
Yeah, it's a horizontal reflection. So let's make that statement formally. The rest of this section is just going to be you graphing exponential functions and their transformations. So the last sort of observation here is that, I'll say it in general, if f of x is a to the x, then g of x equals 1 over a to the x is the horizontally flipped version of f of x. And this is because f of negative x would be a to the negative x, which would be 1 over a to the positive x, which is g of x. So like 1/3 to the x is the same as 3 to the negative x. Right? And remember that when you multiply on the inside by a -1, f of negative x is the horizontally flipped version. So let me,
What's the word after horizontally flipped version of f of x?
oh, because. Yeah, because. So if I have over here a to the x, this is 1. And maybe up here somewhere is a. And the graph a to the x. Two. This would be 1 over a, so 1 over a squared. So this would be like f of x equals a to the x. And the horizontally reflected version this would be like g of x equals 1 over a to the x. So the orange here would be an example of exponential decay. And the purple here would be an example of exponential growth. And all exponential graphs, every function that can be written like some constant to the x, has a graph that looks like one of these two things. I think we are about out of time now. So let me just tell you that the remainder of the problems and stuff I'm going to ask you guys to do in this section really is just graphing exponential functions and their transformations. So you need to get comfortable plotting points and get comfortable with what these shapes look like. You'll always have a horizontal asymptote. And if you're just looking at a to the x, that will be y equals 0. If you're looking at a growing exponential where a is bigger than 1, you'll approach that asymptote on the left. If you're looking at a decaying exponential, then you will approach that asymptote on the right. And then, of course, I can shift these up and down. I can shift them left and right. I can flip them over horizontally, vertically. We can stretch them and all of that good shit. And that's what you'll be doing in your homework set here. It's nothing too hard. It's just more practice with transformations. Next time, I'm going to show you logarithms, which are the inverses of these things. And then we'll be talking about shifting them around. And once we are comfortable with the definitions, graphs, and properties of exponential and logarithm functions, we will start worrying about equations involving these sorts of things. So like, how would you solve the equation 2 to the x equals 5? Turns out, not entirely obvious. So that's where we're going, and it's going to be a quick section, so a quick unit here. So I want to just in parting show you how soon exam 3 is going to happen. Exam 3 is going to happen very soon. The gap between exam 2 and 3 is short. Exponentials, natural exponential, logarithms, rules for logarithms, equations, and then exam 3. So we're talking like 2 weeks max between now and exam 3. Okay, it's going to go very fast. So please stay on top of the homework. I'm going to publish a new homework set for you today. And don't fall behind here. We're going to move quickly. I know this is stuff most of you have seen because the previous algebra class, wherever you came from, high school, college algebra, somewhere else, required this stuff. So we're not going to loiter here. There's not a lot of new stuff between this and college algebra. It's just going to be a little bit deeper, and I will be expecting you guys to be a little bit better at it than you were before. If you didn't really learn this stuff in college algebra, now is the time to fill those gaps. So don't cheat yourself. Please work this homework, work it honestly and earnestly, and you will be okay. Just be aware exam 3 is coming faster than you think. All right, I got to get running. Take care, guys. I'll see you on Monday of next week. Bye.